Oil is a key factor in the world economy. Its transportation around the world is nowadays a major industry. However, the escalation in the price makes the cost of crude oil itself by far the most significant factor in deciding where to obtain supplies. But it wasn't always so, and it's not so today for other products. Cement, for instance, is a relatively cheap commodity. This means that the cost of transporting cement from factory to customer is a significant proportion of the total cost. And this is also true for oil products from the refinery to the local depots. Now, in such circumstances, it's important to keep the cost of transportation to a minimum. And it's this problem which will concern us today. Well, here's a fairly basic example which I'm going to work with. I'm supposing I've got 3 factories, and I'm looking at their maximum outputs, which are respectively 4, 7, and 6. Then over here we have 2 customers, and they have certain requirements. We have 8 and 9. Now you'll notice at once that the maximum output, 4 plus 7 plus 6, well, that's 17, which is exactly the same as 8 plus 9, the requirement. Now the transportation costs from each factory to each customer will depend upon the distance and upon various other factors. What we're going to do is to look at the cost per unit, as I say, the cost per module. And so we have 5, 4, 3, 3, 2, and 5, respectively. So here then is the essential bits of our model. We've got certain outputs, certain requirements, and we know the cost of transporting one to fulfill the other. Now, of course, any real-life problem would be much larger than this. And also we've made certain simplifying assumptions, but never mind, we've got here all the essential features of the problem. Well, let's see if we can solve this problem just by using common sense. Well, how about the first customer? His requirements are 8. Well, the first factory can supply him with just 4, so then he wants 4 more. Let's take them from the second factory. So there's the next 4 units. And now that leaves only 3 from this factory. We'll give those to the second customer. He wants 9 altogether, so he wants another 6, which of course is precisely what we have here in this last factory. So what have I actually done? Well, I've got a solution, but I didn't pay any regard at all to costs. Now, if you actually work out what the cost is, it's going to be 5 times 4 plus 3 times 4 and so on. If you work out the answer, it turns out to be 53. Well, this isn't going to be the cheapest. So what should our strategy be? To find the optimal solution, that's to say the cheapest solution. And bear in mind that in a real-life problem, you're going to be faced with many thousands of factories and probably thousands of consumers. Well, here is Norman Biggs of Royal Holloway College, who will take up the story.
Well, there's a fairly simple method of solving the general problem, and our example here will serve to illustrate it. First, as you might expect, we replace this lovely model by our usual kind of graph, with the factories, consumers, and costs represented in the obvious way. Now, to begin, we want what we call a feasible solution. That is, just any solution which satisfies the conditions of the problem. And a good way of doing this is to select the cheapest routes available at each stage in turn. Cheapest route of all is Cn, so let's use that for all the 6 units produced at C. The cost so far is 2 times 6, and 3 units are still needed at N. Now, the cheapest way of supplying N would be to take those 3 from B at an additional cost of 3 times 3, and leaving 4 units still available at B. Now, those 4 must go to M, so that gives us an additional cost of 3 times 4, and at M we still need 4 units. These must come from A, so we have 4 units going along AM at a cost of 5 times 4, and the total cost works out at 53. Now, this is our first feasible solution of the problem. You'll probably have noticed, in fact, it's the same one that Roy found. Our question is it the best solution? And if not, how can we improve it? Well, it's fairly easy to see that if we use just these 4 routes, then no further improvement is possible. If we want to improve our solution, then we shall have to bring into use the 2 routes, Cm and An, that we haven't used as yet. let's look at Cm. Now, if I decide to send 1 unit along Cm, because the production at C is fixed at 6, I can no longer send 6 units along Cn, I can only send 5. And that leaves n, of course, 1 short, which I must make up by changing the amount sent from B to n from 3 to 4. Now, of course, B produces 1 less available, and so the amount going from B to M must be changed as well, and that must be reduced to 3. Now you'll say, well, M is 1 short, but in fact we're all right now, because the original unit we sent along Cm makes that up. So we have a new feasible solution, and this time the cost works out to be 56. Well, that's 3 worse than the original solution, so much for that idea. But anyway, let's not despair. We still have to try the route an. The first thing to do is to reinstate our original solution, like this, and then to apply the same trick as before. If we send a unit along an, we have 1 less to send along am. We have to send 1 more along bm, and 1 less along bn. And here we have another feasible solution. This time, the cost works out at 52, and that's 1 less than the original cost, so in fact we have an improvement, and perhaps our idea wasn't so bad after all. Well, 2 things to notice at this point. First one is that although our original solution was worked out by taking the cheapest route available at each stage, it didn't in fact give us the best solution overall. We've just found a better one. Second thing to notice is that these calculations I've just done could be simplified if we simply concentrated on the changes involved in the cost. What I mean is this. If we denote by little c of an the cost of sending a unit along an, then the change in cost as a result of sending 1 unit along an and making the other changes is cost of an minus the cost of am plus the cost of bm minus the cost of bn, which is 4 minus 5 plus 3 minus 3, which is minus 1. And so, as we saw, there is a decrease in cost of 1 for each unit rerouted along an. Now, you'll probably have noticed that we could, in fact, do better by rerouting more units along an. How many should we divert, and how much better could we do? Well, before we come to that, Roy is going to give us a rather better way of making these calculations. If we had a large network with hundreds of consumers, then our rather haphazard approach wouldn't be too practical.
Well, what we do is to suppose that each transportation cost can be shared between the factory and the consumer. Well, let's take the first route AM as an example. We imagine then that the cost of AM can be shared between a dispatch cost at A and a receipt cost at M. And these are both known as shadow costs. And we can do the same thing for the other 3 routes in use, for BM, BN, and CN. And this shows also the other dispatch costs at B and at C, and the other receipt cost at N. Now, if we put in the values that we know about, the values of AM and so on, 5, 3, 3 and 2, we've got a set of equations. But there is a snag, apparently, because we've got 4 equations and 5 unknowns. Nevertheless, you can get values. You assign one arbitrarily. Let's suppose I put the cost at A equal to 0. And then if I put this in the first equation, this will tell me that the cost at M must be 5. Putting that in the second equation, I can get the cost of B. I only want 3 altogether, remember, and so the cost at B must be minus 2. Then, from the third equation, I can figure out the cost of N, which will have to be 5. And finally, putting that in the last equation, I get the cost at C. I've got to make 2 altogether, and so this must be minus 3. Now you'll notice that the cost at B and the cost at C are negative. Now what on earth does this mean? It means actually that instead of a cost, we have a benefit, at least relative to the cost at A. Because if you use just these routes, it pays to dispatch from B or from C rather from A. Now you might also notice that we could have solved the algebra directly without the equation. We could have done it on the network. For example, once you've got as far as knowing that the cost of M is 5, since you actually want 3 here, you can see immediately the cost of B ought to be minus 2. Now such calculations can always be carried out provided only that the network of used routes forms a tree. There mustn't be any cycles. Now this implies that you must always have one less route in use than the total number of vertices in the network. Well, what have we done so far? We've completed 2 stages. We set up a feasible solution, and now we've introduced the notion of shadow costs. Well, let's proceed with the next step.
Well, remember, the shadow costs have been worked out in relation to our original feasible solution. And now we're going to use them to see whether it can be improved. What we do is this. Here are the shadow costs and the 2 routes AN and CM, which we didn't use in the original solution. The shadow costs tell us that the cost of supplying 1 unit at A and receiving it at N in the original solution was 0 plus 5, that's 5 altogether. And remember that in that solution, no units were sent directly from A to N. If we had sent a unit directly from A to N, the cost would have been only 4. Well, that's the content of this equation. The cost of using AN less the sum of the shadow costs at A and N is minus 1. So we have a benefit of 1, a reduction in cost of 1 for each unit diverted along AN. For CM, the same calculation. Work out the cost at CM minus the sum of the shadow costs at C and M. We get plus 3. And so there is an increase in cost of 3 for each unit diverted along CM. And of course we conclude that it's beneficial to bring AN into use, but not CM. Now the question I asked a few minutes ago. How much should we divert along AN in order to get the best possible solution? Well, remember that for each extra unit that goes along AN, 1 less must go along AM, 1 more along BM, and 1 less along BN. And the original amounts that were sent along those routes are 4, 0, 4, and 3. And it's this last 3 that is the important thing. Because, you see, we cannot take away more than 3 units from the amount going along BN without changing the solution. So that's the answer to our question. The most that we can divert in this way is 3 units along AN. If we do that and make the resulting changes, we find this feasible solution here. The cost of it is 50. Well, that's our best solution yet, but is it the best one possible?
Well, first of all, let me remind you of what we've done so far. Well, we began by finding a feasible solution. This meant satisfying all the requirements but ignoring transportation costs. Next, we split the transport costs, each into 2 parts, by the device we call shadow costs. And then from these shadow costs, we were able to calculate the effect of bringing a new route into use. Now we found this was beneficial, and the most beneficial new route was then exploited to gain the maximum benefit. Well, this gave us a new solution, still satisfying all the requirements, but at a reduced cost. Well, the question now is, can we do even better by introducing a further new route? Well, this is where we came in. We've got to go back to step 2. We must recalculate the shadow costs, because you see, they depend on the routes actually in use. Well, once more, it's in step 3, in which we examine the effect of introducing these new routes. And what about the routes BN and CM? Now, the formula tells us that if we use either of these routes, it would only make things worse. You see, the costs will rise by 1 unit for each module of goods transferred onto the route BN, and by 2 for each module transferred onto the route CM. So we find it isn't beneficial to use either route. Well, there aren't any other choices. This means, therefore, that no improvement is possible. A Norman solution is optimal. Well, our example is very simple, but it's adequate for our present purpose. Now, you'll notice, as I said, that the customer requirements are exactly matched by the available output. Well, what would happen if the total output were less? Well, then, of course, there wouldn't be any feasible solution. But if the output exceeded the requirements, well, all we need to do is to divert the excess supply to a dummy customer to whom all the transport costs are assumed to be zero.
You're probably wondering why this algorithm works. Well, it's a good question, and fortunately it's possible to give a geometrical interpretation which throws some light on it. Let's go back to the original problem and make a table showing the essential information: the supply, the demand, and the costs. Now, the first thing I'm going to do is to suppose that we send X units from A to M and Y units from B to M. The reason for doing that is that the constraints of the problem now determine all the other amounts. For example, since A produces just 4 units and X of them go to M, the remaining 4 minus X must go to N. Same way, from B to N, we must send 7 minus Y units, and looking at M, well, it's already received X units from A and Y units from B, so it must receive 8 minus X minus Y units from C in order to make up its demand of 8 units. And for Cn, we find the amount required in the same way. So here is the general feasible solution to our problem. Now, the cost is quite easy to calculate as well. If we send X units here at a cost of 5, the cost is 5X. If we send 4 minus X units here at a cost of 4, the cost is 4 times 4 minus X, and so on. So the total cost is the sum of all these terms, and that works out at 73 minus 2X minus 3Y, so I'm told. So now we have our problem expressed in just the two variables X and Y. What we have to do is minimize this total cost, 73 minus 2X minus 3Y, under certain conditions. And we can make a simple model of the problem like this. I've drawn axes for X and Y on the surface of the table, and I've tried to indicate that not all values of X and Y are possible. If we look back at our table, we'll see that since the flows from A, that's X and 4 minus X, must both be non-negative, it's necessary that X must lie between 0 and 4. That's here. Similarly, looking at the flows from B, we see that Y must lie between 0 and 7. And looking at the flows from C, we find that X plus Y must lie between 2 and 8. Well, this means that the feasible solutions to our problem correspond to this region on the table, and we call this the feasible region. The costs are quite easy to indicate. Looking at this point, X equals 2 and Y equals 0, we can indicate the cost, 73 minus 2X minus 3Y, which works out at 69 at that point, like this, the height of a vertical rod indicating 69. At this point, for example, where X equals 0 and Y equals 2, the cost works out at 67. We can indicate it like that. We could indicate the cost at every point of the feasible region in the same way. I've put in just a few more of the rods. When we did that, we would find that the tops of all the rods lie in a plane. Now, remember our problem. It was to find the cheapest solution, and that would be the lowest point of the plane corresponding to a point of the feasible region. With the model, the solution is fairly obvious. Here is the cheapest solution. Now let's think back to our algorithm and try and interpret the steps of the algorithm in terms of this model. Probably remember the first thing we did was to find just a feasible solution. And in fact, it was this one, corresponding to the point X equals 4 and Y equals 4, where the cost turned out to be, in fact, 53. Then we tried making some small changes. The first thing we did, in fact, took us to this point where we worked out the cost and found it was greater. We've gone up the plane. Next stage, we tried moving in this direction. We worked out the cost and found an improvement. We've gone down the plane. We've done that. We introduced these mysterious shadow costs in order to see how far this improvement could be maintained. You may remember that one application of that calculation led us immediately to this point here. Then Roy repeated the entire shadow cost calculation again, starting from this point, and he found, sure enough, that any changes we made here result in moving up the plane. So this is our optimal solution. Well, of course, a simple model like this only applies when the problem can be expressed in terms of just the two essential variables, x and y. For a larger problem, the same kind of ideas would still apply, provided, of course, that we could visualize a model in the right number of dimensions. But the beauty of mathematics is that it enables us to prove that our algorithm always works.
Well, here again, we have the flowchart for our algorithm. Now, this is, of course, not the same as the Hungarian algorithm that you find in the text, because that has a different flowchart, and here it is. Well, you're quite right. Both diagrams do have the same block structure, but, and it's a big but, the course of the algorithm is entirely different. For example, look down here at the test condition. To ask if the required flow has been reached is just the same thing as saying, is the solution feasible? Now, finding a feasible solution was the very first step in our earlier algorithm, do you remember? But the Hungarian algorithm finds a feasible solution only at the very end. It finds the optimum in an entirely different manner. You might say it approaches the problem in reverse. However, if you care to apply the Hungarian algorithm to our simple problem, you will find it reaches precisely the same solution as we did. Now, it may not be obvious that the Hungarian algorithm does always produce an optimal solution, but at least we know that it does with our example because it reaches the same solution as the previous algorithm. Well, is there any reason for choosing one algorithm rather than the other? Each has its merits. The first algorithm is probably easier to work by hand, but the Hungarian algorithm tends to be more efficient, and so it's well suited to the solution of large-scale transportation problems, particularly with the aid of a computer.